And now energy equation. The first law of thermodynamics applied to a fluid passing through an infinitesimal finite fixed control volume yields the following energy equation. Derivative of rho E with respect to t plus scalar product of nabla operator and rho EV equals to dq by dt minus scalar product of operator nabla and q plus rho f dot v plus scalar product of nabla operator and p dot v. Here E is the total energy per unit mass, and given it is given by the following expression, where E is the internal energy per unit mass. The first term on the left-hand side of equation 1.39 represents the rate of increase of E in the control volume, while the second term represents the rate of total energy lost by convection through the control surface. The first term on the right-hand side of equation 1.38 is the rate of heat produced per unit volume by external agencies, while the second term nabla dot q is the rate of heat lost by the conduction per unit volume through the control surface. Fourier's law for the heat transfer by conductions will be assumed, so that the heat transfer Q can be expressed as Q equals minus lambda gradient T, where lambda is the coefficient of thermal conductivity and T is the temperature. The third term on the right-hand side of equation 1.39 represents the work done on the control volume per unit volume by the body forces, while the fourth term represents the work done on the control volume per unit volume by the surface forces. It should be obvious that equation 1.39 is simply the first law of thermodynamics applied to the control volume. That is, the increase of energy in the system is equal to heat added to the system plus the work done on the system. For a Cartesian coordinate system, equation 1.39 becomes the derivative of rho E with respect to t minus d capital Q by dt plus the derivative with respect to x, y of the following expression rho e u I plus p u I plus q I minus tau I j multiplied by u j is equal to rho fi u I, which is written in conservation law form. We can write this equation in more details without using Einstein notation. You see this very long expression. Using the continuity equation, the left-hand side of equation 1.39 can be replaced by the following expression. Rho capital D E by dt equals d by dt of rho e plus scalar product of operator nabla or divergence and rho e v, which is equal to the following expression. If only internal energy and kinetic energy are considered significant in equation 1.40, this is true. This expression is true. Forming the scalar dot product of equation 1.30 with the velocity vector v allows one to obtain the following expression. If equations 1.44, 1.45 and 1.46 are combined and substituted into equation 1.39, a useful variation of the original energy equation is obtained. The last two terms in this equation can be combined into the single form since the following expression is true, where T double dot V and operator nabla V is the double dot product of two tensors. It's a scalar. This term is called the dissipation function phi and represents the rate at which mechanical energy is expanded in the process of deformation of the fluid due to the viscosity. After inserting the dissipation function, the equation 1.49 becomes the following: rho capital D E by dt plus P dot product of operator nabla and V equals to dq by dt minus divergence of q plus dissipation function phi. Using the definition of enthalpy, H equals E plus P divided by rho, and the continuity equation, equation 1.49 can be rewritten as the following: rho capital D H by dt equals capital P by dt plus d q capital Q by dt minus Nabla operator dot q plus phi. For a Cartesian coordinate system, this dissipation function becomes the following: if the flow is incompressible and the coefficient of thermal conductivity is assumed constant, equation 1.49 reduces to the following form: P rho capital D E by dt equals d capital Q by dt minus lambda Laplacian of t plus dissipation function phi.